Okay, today I'm going to formalize a little what the book calls verifying an identity. And I'm going to do that first by showing you the wrong way, because you may be tempted to do this the wrong way. We want that. Okay. So I have an identity here, and I want to verify it, its truthfulness. I look at this and I go, this is the problem here. I should have a new symbol. I'm going to create a new symbol. Like that. Because we don't know these are equal. We're trying to find out if they are. And when we're trying to demonstrate something in math, a very, very bad place to start is by assuming what you're trying to prove is true. That can get you in all sorts of trouble. But for the moment, let me remove that and say, all right, well, if these are equal, I can cross multiply, right? Everybody remembers cross multiply? And I go, okay, sine squared theta, and then I have 1 minus cosine and 1 plus cosine. Well, that's difference, I just erased it, difference of squares.
What are you doing?
I'm cross multiplying. Everybody remember fractions?
Can you give us a word refresher?
I want to find x. So I cross multiply. 2x equals 3. 2 times x equals 3. So x equals 3/2. That's usually how you use it. Okay, so I take the next step and I add cosine squared to both sides. And I get something that I recall is an identity. So I say, aha, this must be true. But as I said, in this case, you really wouldn't get into much trouble. But this is not the way to verify an identity. Because we're assuming this is correct. And using the fact that it's an identity to show that it's an identity doesn't work. Instead, the orthodox way to do this, the proper way, is if you have two expressions, call them expression A and expression B, and you want to verify this as an identity, you take each of the expressions, do what you will with them, change them, and get it down to where they're both equal. Now, the reason this works is because whatever steps you take to get here are valid. Whatever steps you take to get here are valid, or hopefully reversible. If they're not reversible, this doesn't work. And so I've gone step, 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 and I've shown that I've shown that the identity is correct. Now, this actually could be A. You don't have to do anything to this side. This could be B. You don't have to do something to this side, as long as you get to where the two are equal, without playing games like cross multiplying or adding to both sides or subtracting from both sides. Because in order to do that, you have to assume the identity, which we don't want to do. Okay. So that's kind of the formal way of doing this, and I will follow it. Letter. So let me give you an example of how we want you to verify an identity. I'm going to start with this one. Cosecant theta tangent theta equals cosine theta secant squared theta. And, you know, when you've done enough of these, you can take a look at them and you can make a judgment call. You know, you can say, gee, secant squared, that maybe I can use one of these identities and flip it around. But I'm just going to use the straightforward method, which is convert everything to sines and cosines. So my cosecant becomes 1 over the sine of theta. My tangent becomes sine of theta over cosine of theta. And then my next step, I'm just going to have 1 over cosine of theta. On this side, I do the same thing, where I have cosine of theta times secant squared. That's 1 over sine squared theta. Did they give me a bogus example? No, it's not. Because secant squared is 1 over cosine squared. All right. I cancel one of the cosine squares, and I get cosine theta. And lo and behold, they're equal, so I have shown this identity is correct. All right. I'm going to do another example.
Could you actually use the seating to other board? I didn't finish writing down the example you showed.
I mean, there are 9 boards, just saying.
I will comply, but so you know why I'm trying to use the only 3 is I was trying to make, I was told last week that if I zoomed in, the videos would be better, but I can only zoom in if I use one board. Tough luck for people who aren't here. Right?
I mean, if your view count's higher than the amount of students in this class, I fully support that. But if it's less than that, wouldn't it be more beneficial for us to all be able to see?
I'm with you.
Excellent.
What I need is a cameraman, right? Somebody to go switch the camera.
Is it still possible if I can see the problem behind the board? Yeah, that's all I wanted.
This one?
Yeah, the one, yeah, that.
That's all you ever wanted.
Thank you.
Okay, one more here. Cotangent squared theta equals cosecant squared theta minus cotangent theta tangent theta. I'm not going to use the standard techniques, the sines and cosines, because I can see something a little simpler here. Here I'm just going to do nothing for the moment. But on this side, cotangent I'm going to write as cosine over sine. And tangent I'm going to write as sine over cosine. And of course, both of these cancel. This becomes 1. And then I'm going to use Pythagorean. No, that's over here, isn't it? Cosecant squared equals cotangent squared plus 1. So that's cotangent squared plus 1 minus 1 equals cotangent squared. And then just one more step and my 1 disappears. Okay. These are so much fun for me. I'm going to give you a handout. We're going to do the first 3 on here just to the first page. Let's work on these for a few minutes. I'll get to the. One, two, and three.
How do you do the last step of that problem? I didn't follow exactly.
Well, the last step, I just subtract one from one.
Well, I'm saying instead of four out.
So
How do you
pass
get
them
the,
to the people. One
how
more.
do you get the plus one?
Let me get back up to the board to pass this over to Stanley. Everybody has one? So I'm here, cosecant squared minus 1, right? Here's one of my identities. Cosecant squared equals, pardon me, written differently,
Cosecant replace.
cotangent squared plus 1. So I just replace cosecant squared with cotangent squared plus 1, and I said, you know.
But just as a, by the way, the cotangent is CTN instead of COT.
It's both.
Oh, it's both?
It's either. Yeah. Co-tangent or co-tangent. They're both the same.
So what do we actually accomplish here? We just wrote cotangent squared equals cotangent squared, which is kind of like the current.
So what I've done is this is what I'm trying to verify.
So you're just proving.
And I worked on both sides, except I didn't do anything to this side. And I end up with an equality which shows me that, which verifies the identity. It wasn't first that we were in.
Yeah.
Oh, sure. Yeah, that was right. Okay. Right. So you have, cosine squared over sine squared, 1 over sine squared minus 1. Well, let's do something with this. Let's put this all over sine squared. One minus sine squared. We can use the Pythagorean identity on that and get cosine squared. All roads lead to.
No, I knew it would have worked, I just wanted to check myself.
There's something similar.
No, I was doing one of the boards.
Oh,
the longest way, so I
You're done already, right?
Or is it,
Oh, you're tired. Oh, okay. All right. I wasn't trying to be like a mean high school teacher. Coffee time. Running. Any identity in the process. Verify.
That happened. Interpretation.
I'm going to put number 1 on the board.
Is that a hard one?
I didn't say I'm going to do it. I'm just going to write it on the board
So, Sean, you know
in anticipation.
You know you're good? Vaguely. Yeah, that's reassuring.
Cotangent squared theta. Cosine squared theta equals sine squared theta. Okay.
Is the answer ever going to be no? It's not possible.
In this class.
Yes, it is. It is possible.
On the sheet.
Only if I made a mistake. I did not
It
intend.
should be solvable.
It was not my intention. But I am fallible. When it comes to math, we're all fallible. You just have to learn to self-correct. That's a very important thing to know in mathematics, you know, when things aren't going right, what to do about it. Other than, you know, run from the room screaming with your hands waving. That works well. Although it could feel good.
If it was tangent, you could just cross out cosine, cosine, do up with sine squared, and then it'd be all fine tangent, but cotangent, cosine, cosine. Is he gonna do that? Yeah. He just wrote it, but he didn't do it.
You know, these are funny. You can really like go really totally the wrong way and still have it work. Okay, you go totally the wrong way here. You say, well, secant squared times cotangent squared is 1. Well, this is multiplied by 1. So this is sine squared theta squared theta minus sine squared theta cotangent squared theta. Cotangent squared theta sine. Now, secant 1 over the cosine. Oh, so that's tangent squared minus. Uh-oh, that's not going to work. Maybe you can't go the wrong way. I don't know. I'm not going to pursue that, even though I think it'll work. Anyone stuck on this still?
If you change the cotangent to tangent, the problem would work out.
You can't do that.
No, I just feel like it was written wrong.
Oh, maybe. So let's see, this is
is, oh, cosine squared theta over sine squared theta times cosine, maybe it's wrong. Actually, it's not wrong. I wrote it down wrong, maybe. All right. Well, let's see if we can, let's see what would happen. Let's see what would happen if we were to get something that isn't really true. Let me at least try something with this. How about cosine squared theta times 1 minus sine squared theta over sine squared theta. Right? So that's going to be cosine squared theta over sine squared theta. Oh, it just gets me back where I started from. No, that's not good.
There's a huge difference when we let that alone in that.
It doesn't look very good, actually. It looks like it's not true. How do we really show that it's not true?
Just flash through the equal sign rule right here.
Well, what I did is if you combine the cosines, so you have cosine to the fourth of theta, and then multiply the sine to the other side, you get cosine to the fourth equals sine to the fourth, and that's false.
Say it again.
So combine the cosines, so you have cosine,
I'm sorry, start over slowly.
so you have it split up into sine and cosine. Combine the
Where? Here?
Yeah, right there. Combine the cosines. So you have cosine to the fourth of theta
Cosine to the fourth theta, right?
over sine squared theta equals sine squared theta. And just multiply the sine squared theta to the other side.
Yeah, this is one case where if you're looking and you think it might be wrong, clearly,
That can't.
yeah, that can't
That's
be.
just not true.
So, I thought I wrote this down from the book. That'll teach me. Yeah.
Can you verify what I did here? I got it to be equal to, I don't know if it's right.
Good. Good. Or bad.
I don't know if it's, well, I just
Oh.
want you to verify.
Okay, so 1 over tangent square. Cosine square. You. You can't do that because it's this minus 1. That's a fraction. Okay, that's all right, well, on to 2, please. Apparently 1. I'm going to look for that.
Yeah, we knew you, I knew you were trying to. I only got one question.
Hey, now, wait a minute. Wait a minute.
I did. Where do you want to start with next to the office?
There's another one in the book. There's another one in the book just like it. The one in the book says cotangent times cosine equals sine.
Yeah, you gotta get it.
It's the same problem.
Wait, didn't you just say cotangent times sine equals sine?
No, look at number 1, 701.
No, it's that's not.
So that's just cosine over sine times cosine equals sine. Right? Well, this one this is cosine squared, so I could make that 1 minus sine squared over sine.
minus 1 equals sine. Well, that doesn't look very good, does it? Because this could be a huge number, right? Minus 1. Sine can only be between -1 and 1. So this is wrong. I wonder how this snuck in here. All right.
I think we should Google it first.
It's wrong. Oh, well, you know, actually, there's something I really didn't go over, which I think is really worthy of mentioning. All right? Let's take our original wacky problem that apparently is wrong. Right? So in mathematics, proving something can be very hard. But disproving something can be very easy. Let's see if we can, how do we disprove something? How can we disprove something in mathematics? We find a counter example. You only need one counter example to prove something isn't true. So let's just try some things here. How about theta? Put theta here. Let's just try 0. So the cosine of 0 is 0. The cosine of 0 is 1. Oh, wait, that worked, didn't it? Cotangent of 0 is, it's undefined. Right, so that's not really a good one. How about pi over 2? How about pi over 4? All right. So sine squared of, what's the sine of pi over 4? So 1 over the square root of 2. So squared, just 1/2. What's the cosine squared? Same thing. Oh. That's 1. Uh-oh. Now, maybe I just picked bad examples. That's possible. Pick the worst possible examples. All right. How about pi over 3, or 60 degrees? This ought to flush it out, unless it's true. Okay, does anyone remember what the sine of 60 degrees is?
Root 3 over 2. Root 3 over 2.
Root 3 over 2, but we're going to square it. Cosine squared is going to be 1/2 squared. This is cosine over sine.
1 over root 3.
1/2 over root 3 over 2, right?
Yeah, 1 over root 3.
Squared. So, this is 1 over root 3 squared times 1/2. Oh. Be quiet. So this is 1/6 equal to 3/4. Really not true. So that's our counter example.
I think the one in the book, question 1, is cotangent squared times sine squared equals cosine. And that came from 1,
I don't know where I got it from. Maybe I wrote it down. All right. Why don't we move on to number 2, if you haven't already. something that doesn't work, you have to work harder, which is, what I want you to do. You have to work harder to show something's not true, right? Okay. Might as well write it on the board. You're not stuck already, are you? Or you finished already?
No.
Well, no, you could do 1 over 1 plus cotangent plus tangent over 1. Do that. So 1 over. I mean, I think you know this, but. That's all I'm doing. But you can't break up the denominator that way.
So then this would be.
Yes. Tangent over that, yes. All right, someone want to tell me where I might start with this one?
Convert cotangent?
Convert cotangent to
Cosine over sine.
cosine over sine over, okay. Ooh, this looks like a fraction, doesn't it? Looks like a fraction I want to put over a common denominator. I mean, a sum I want to put over a common denominator, doesn't it? What would that look like? Cosine plus 1?
Oh, no, sorry, cosine
Plus sine theta
over sine.
over sine. All over cosine theta plus sine theta. Oh, but dividing, I have cosine plus sine, and I'm dividing by cosine plus sine. That just leaves me with 1 over sine.
Where'd that come from?
Wait, my algebra's pretty rusty. Could you,
Oh boy, uh-oh. Okay, so I've got A over B, I'm sorry, all over A. Okay? So to divide by something, you multiply by its reciprocal. Okay? So there I go. I got 1 over sine. Oh, what's the cosecant? That's 1 over the sine. So again, you know, if you're thinking proof, you think, well, cosecant is 1 over the sine. 1 over the sine is equal to this, and so forth, back up to the top. Yes?
Can you show how that's equal to 1 over sine?
Can I show how cosecant is equal?
No, the cosine plus sine over sine squared divided by cosine.
That's what I wanted to.
Okay, let's do it step by step. We converted cotangent to cosine over sine, right?
How do you know to do that step instead of, for instance, replacing cotangent plus 1?
Well, it's not cotangent squared plus.
Oh, okay.
Right.
Yeah.
The way we do to do this is because without any other idea, we convert everything to sines and cosines and see if things simplify. Okay, so cosine over sine plus 1 that's just cosine over sine plus sine over sine. And now I have a common denominator, so it's just cosine plus sine over sine. And now my numerator of this fraction is the same as my denominator of this fraction. So I can just get rid of it. I like this. I could do that if you want. I could say, put in another step here. Cosine of theta plus sine of theta over sine of theta. So I'm dividing by this, so I multiply by its reciprocal. And I'm just going to cancel that. Questions? Okay, I'm going to leave number 3 for later, but I do want you to listen real closely now. There's a whole slew of new identities we're going to go over, but really only 2 of them are kind of tricky. I'm going to show you how we get one of them, and I'm not going to show you how we do the other one, because some of you are going to get lost when I show you how to do the first one. But those of you who can hang in there, there's a couple things I want you to remember. One is a theorem from geometry which says if I have 2 arcs, you know what an arc is, on the same circle, and if those 2 arcs are the same length, then their chords are the same length. Okay, that's probably all you need to know from geometry.
Sorry, what was if the 2 arcs are the same length?
In the same circle,
Okay.
the arcs are equal, chords are equal.
What's the arc again?
Arc is a part of the circle between, we'll say, point A and B, and say point A prime and B prime. So if the length of AB of arc AB is equal to A prime B prime, then their chords have to be equal. Okay?
Okay.
Ready? All right, here goes. I'm going to draw a unit circle. I'm going to put some points on it. This is point A. is at 1, 0. I'm going to put a point Q, and I'm going to put a point P. So the arc from AP, I'm going to call R1. And the arc from PQ, I'm going to call R2. And then I'm going to draw this line AQ. And now I want to think about what are my coordinates for Q. Well, if you think of this angle here, right? This angle has, intercepts this arc R1 plus R2. But since it's a unit circle, that's the radian measure of that angle, right? So for point Q, it's just cosine of R1 plus R2, sine of R1 plus R2. That's Q. Now, I'm going to construct one more point, which is called, I shouldn't use that letter, but I will, capital R. And I'm going to construct R such that this arc here is also R2. So now, I'm going to draw this line PR. And if you look carefully, AQ is R1 plus R2, and PR is R1 plus R2. Which means that the two line segments are the same. Okay, let me write down the coordinates of R. Okay? Now, again, we've got an angle here, R2, which is negative, this angle. So this is the cosine of negative R2, sine of negative R2. And then the last point I have to figure out is P, right? Well, again, there's an angle here for P. So P is the cosine of R1 sine of R1. Okay, so I've got a bunch of points. I've got a bunch of coordinates. Now I'm going to use the fact that QA and PR are equal. So what I'm going to do is I'm going to use the distance formula, or the Pythagorean theorem, if you like. First, let me work on AQ, right? So Q is cosine R1 plus R2, sine R1 plus R2. So the x coordinate, cosine R1 plus R2 minus the x coordinate of A is 1. I square that, and here I take the sine of R1 plus R2, and I subtract what? I subtract 0, because that's the coordinate of A. I square it, and I find the square root, and that's my distance QA. Everybody see that? I'm just taking the coordinates I wrote down, and I'm finding the distance between those 2 points. I'm going to do the same thing with PR now. All right? So I get cosine R1 minus cosine negative R1 squared plus sine R1 minus sine negative R1. The whole thing is squared. Okay, so I'm just saying, all I'm saying here is QA is equal in distance to PR. From here on, it's a little complicated, and then
you simplify.
From here on, it's complicated?
Yeah. Okay, so what am I going to do when I have the square root of this equal to the square root of that to simplify? I'm going to square both sides. No big deal. That's pretty simple. Cosine R1 plus R2 minus 1 squared plus sine squared R1 plus R. Keep writing these different ways. Do that equals cosine of R1 minus cosine of... You won't have to reproduce this anywhere, anytime in the future. Like,
Can you just write the identity and then continue proving it?
Hmm?
Can you just write what the identity is in its final form and then we'll get to the...
I could, but that would really interrupt stuff.
Okay, so we'll
Just hang in there. Just hang in there. Oh, there's a 2 here, sorry. Okay, so now I'm going to multiply these things out and see what cancels. All right? So I've got cosine squared R1 plus R2 minus 2 cosine, this is FOIL, R1 plus R2 plus 1 plus sine squared R1 plus R2. I'm going to skip the other side for just a second. Does anyone see a nice simplification here already? We got cosine squared plus sine squared are the same thing, R1 plus R2. So that's just equal to 1, right? So we've already got a 1, so I'm going to write that as 2 minus 2 cosine of R1 plus R2. Oh, good. Simplification. Why?
Oh, wait, never mind.
This is already done. Okay. There we have cosine squared R1 minus 2 cosine R1 cosine R2 minus R2 plus cosine minus R2. Oh, you know, I'm going to do something.
Can we take a break?
We're almost done. Then we can take a break. I want to just show you something here. What's the cosine of minus R2? It's just the cosine of R2, right? What's the sine of minus R2? Just minus the sine of R2, so we just make that a plus. Okay, we're almost done. Hang in there. Cosine squared R1 minus 2 cosine R1 cosine R2 plus cosine squared R2 plus sine squared R1 plus 2 sine R1 sine R2 plus sine squared R2. Now I'm going to do that same thing I said before. We're going to look for something to simplify here. Cosine squared R1, sine squared R1, that's just 1. Cosine squared R2, sine squared R2, that's just 1. Minus 2 times cosine R1 cosine R2 plus sine R1 sine R2. Okay, we're almost done here. So I got a 2 on this side and a 2 on that side, right? So I'm just going to get rid of those. And I have a minus 2 times cosine R1 plus R2. I'm going to divide through by it. So what do I get? On this side, I have cosine R1 plus R2. I divide through here, minus 2, and I get cosine R1 cosine R2 minus
sine R1, sine R2. Okay.
Can you like pull down the very top board and then expose the rest of that second board?
I'm sorry, what do you want me to do?
I'd like you to pull down the top board. Exposing that.
There we go.
Voila.
Is that what you want me to do?
Exactly.
Okay, so this is the hardest thing I'm going to show you in this class. But let's look at what we've got here. Let's look at what we've got here. Let's look.
Do we have to?
Only if you're listening. We now have the sum formula. Let me rewrite this a little nicer, without the r's. Cosine of x plus y is equal to cosine x cosine y. I'm going to give these to you on a sheet for the quiz and for the finals, so you don't have to like panic.
What is that?
These are good to know. These are good to memorize, but you don't have to.
What is this identity called?
This is the cosine of a sum. Right? This allows us to find the cosine of a sum in terms of the cosine of each and the sine of each. Oh, you can't read it? If I need to read it bigger?
Underneath your first radical, top right corner, that's the cosine of R1 minus cosine of R2. That would be the left.
This? Over here or over there?
Yeah.
Cosine of -1.
Negative R?
Negative R2.
Okay.
Just to clarify, you aren't going to ask us to reproduce.
Correct.
Okay.
That is correct.
So we just need to write down.
I'm going to repeat what you're saying. You will not have to reproduce this. I merely want to show you, it didn't come out of thin air. Now, there is a corresponding identity for the sine, the sum of the sine. It looks a little different, but it has the same kind of flavor to it. This is the sine of x cosine of y plus the sine of y cosine of x. Okay. We're going to take a break. When we come back, we're going to use these two really important identities to generate a whole slew of good stuff. All right? So go have a break, have a coffee, and get some fresh air. You won't have to think as hard when you come back.
Wait, is this a comment about that guy's comment?
Yeah, like basically just like we need to people looking out and people
What does the theory?
another one is diarrhea. That. What is that?
Well, they meet with you once a week or you
Hey, I
was also thinking of traumatics, of sexual stuff, but I was thinking of I'll give you a hint of what I was thinking of different things.
Well, they're the same expression.
So like it's exactly the same.
And
When you think about fractals, like if this was like 2/3 and this was 1/2,
dissecting stuff.
right? You can cancel it. The only time you can't cancel it
party has long
is
since
if it's in those cases, we don't care for an identity. We're only concerned because it's not defined for a location. It's 1/0, so we don't care.
Well, that would be an awesome prize. But how would you get that in there?
Okay. I know everyone's not back, so we're going to do a little.
And it's
We're not going to do
also-
something critical.
also,
We're going to do a little
So I
exercise.
think there are 5 more minutes left in our break.
Not today.
No.
All right. So I just want to show you something nifty you can do here. So, put these up here for now. So let's say I ask you a formerly very difficult question. What is the cosine of the perfectly manipulated question of 105 degrees exactly? Yeah, I see, Jonathan, you grab your calculator and you will be marked wrong.
1 over square root.
I want to know exactly this.
1 over square, I'm sorry, negative square root.
105.
Did I do math wrong?
We don't know what it is.
So you just sum 60 and 45.
Right.
Yeah, I'm going to say the cosine of 60 plus 45, and that's the cosine of 60, cosine of 45, minus sine of 60, sine of 45. Okay, let's see, what does that turn out to be? The cosine of 60 is a half. Cosine of 45 is 1 over the square root of 2, minus sine of 60, which is square root of 3 over 2. Sine of 45, again, 1 over the square root of 2. That's already the right answer. We could try and simplify this a little. 1 over 2 square root of 2, minus square root of 3 over 2 square root of 2. This is 1 minus the square root of 3 over 2 square root of 2. And if you like to rationalize the denominator, what happens here? This becomes square root of 2 minus square root of 6 over 4. I know Yudi likes to do that, but he's not here. We could do the same thing with the sine of 105, right? Sine of 60, sine of, cosine of 45 plus sine of 45 and cosine of 60. Okay, so sine of 60, square root of 3 over 2, 1 over the square root of 2 plus square root of 2, 1/2. Kind of looks similar, doesn't it? Except it turns out a little different. Square root of 3 plus 1 over 2 square root of 2, or square root of 6 plus square root of 2 over 4. So all of a sudden, the range of things we can find exactly is increased a little bit. Time monitor is time up yet?
Yeah.
Is the break up yet?
Yeah, okay.
Okay. So we have these identities which are going to turn out to be much more powerful in showing other stuff than originally, much more powerful than you'd think. So the first thing I'm going to do is I'm going to get the low-hanging fruit. Anyone know where that comes from?
It's easier to pick the one who don't need a ladder.
Yeah, but where does it come from? Where does that farm? It's a Greek myth. Fox and the grapes. Yeah, it's a Greek myth. Okay, let's try and figure out what would the cosine of x minus y. We had the sum, now we're going to have the difference. Well, we're just going to use what we already know. going to be cosine of, for those who need this step, let me write it as cosine of x plus minus y, right? Okay, so we have cosine of x, cosine of minus y, minus sine of x, sine of minus y. Oh, but we know how to simplify these, don't we? Right? The odd even identities. Cosine of minus y is what? Cosine y. Sine of minus y is minus sine y, so this just becomes a plus. Let me copy this up here. There's a nice symmetry in these, we'll call them formula for the moment, identities. Okay, you guys are pretty smart. What am I going to do next? Yeah. What's the sine of x plus minus y? That's going to be the sine of x cosine of negative y plus the sine of negative y cosine of x. Okay, so we just have to think about what's cosine of y, negative y. Cosine y.
And that's minus sine.
Minus sine of y, so this becomes a minus sine. All right, so now we've just multiplied our nice formula by 2. Okay, kind of a nice symmetry, minus, plus, plus, minus. So, you know, if you could spend a little time thinking about all the new angles that we can calculate exactly. So, what do we have? We know 30, we know 60, we know 90, we know 45. Forget 90. That's not interesting. 45. So we can find the difference of any of these. Well, that gives us 15. 45 minus 30. 60 minus 45 is, oh, it's also 15. The sum, 75. What else? What else can we pull out of there? Well, I guess that's it. That's not that good. I mean, all the negatives, you can always do negatives. 105. Pull a little more low-hanging fruit here. If cosine of x plus y equals cosine of x cosine of y minus sine x sine of y, what if I just set y equal to x? Then I get cosine of 2x, right? X plus x is 2x. Cosine of x, that's cosine squared x minus sine squared x. Oh.
That's nice. It's a nice little double angle formula. Now, actually, this looks a lot like something else, doesn't it?
The Pythagorean?
Yeah, it looks a lot like a Pythagorean identity. If you use the Pythagorean identity, you can play around with this a little. You could plug in for sine squared, which is 1 minus cosine squared, and since we subtract it, you could get 2 cosine squared x minus 1. Or you could do it the other way. You could plug in for cosine squared, and then you get 1 minus 2 sine squared. These are just kind of different versions of this kind of double angle. Okay, another good one. Sine of 2x. Okay. Well, that's just going to be sine of x, cosine of x, plus cosine of x, sine of x. Oh, that's just 2 sine x, cosine of x. So that's a nice, useful formula. We're just pulling the easy stuff out of this. Okay. So now any angle that we have, that we know exactly the sine and cosine of, you could find sine and cosine of double that angle, or quadruple that angle. It'd be nice if we go the other direction, right? Let's see what we can do here. Let's write this guy cosine of 2x in this form. 2 cosine squared minus 1. Okay. Here I'm going to do something that's really simple, but it's like, wow, how did that happen? I'm going to set 2x, and so I don't confuse anybody, I'm going to set it to y. Now I've got cosine of y equals 2 cosine squared, what? That's x. But 2x is y, so this is y over 2. Oh. I'd really like to have a formula for this, but all I have to do is solve for it, right? So let's add 1 to both sides. Let's divide by 2. Now here I have to be a little careful. I want to solve for cosine of y over 2, that cosine squared. So square root, right? But you got to be a little careful here. Let's find the square root of both of these. So this is, of course, just, the cosine of y over 2. But what's tricky about this is, if I was going in the other direction and I square both sides, there could be a minus sign here, right? And it would still work. So when I'm going in this direction, I really need both.
So now I have a formula where I can find half angles, right? Add this to our growing list of useful, I'm going to make it an x here, plus or minus square root of cosine
Cosine x equals?
x plus 1 over 2. There's going to be one for the sine, right? Oh, x over 2, sorry. Sine of x over 2. It's going to look pretty similar, isn't it? Plus or minus the square root of 1 minus the cosine of x over 2. I'm gonna use this side here for these new identities. All right, back to low-hanging fruit. Tangent of x plus y. We don't have to do anything real fancy again, like we did for the cosine and like I didn't do for the sine. I can just use what I know about tangent of x, right? That's sine of x plus y over cosine of x plus y. And let's substitute in what we now know. This is sine x cosine y plus sine y cosine x over cosine x cosine y minus sine x sine y. Okay, well that doesn't look too good, and it would be nice if this was in terms of the tangent. So what could we do to give us just what we're looking for here? Well, what we're going to do to the top and bottom of this is we're going to multiply the top and bottom by 1 over cosine of x cosine of y. We're going to multiply the top and the bottom by this fraction. So we do a little hand waving here. Sine x cosine y, or cosine x cosine y. Well, the cosine is going to cancel. So that's sine x over cosine x. What's sine x over cosine x? Tangent of x. Over here, we're going to do the same thing. Sine y cosine x, or cosine x cosine y. Well, the cosine x's are going to cancel. You know, sine y over cosine y, that's tangent y. Oh, this is going well. Cosine x cosine y over cosine x cosine y. 1. And the minus. Sine x sine y over cosine x cosine y, or sine x over cosine of x. Tangent x. Sine y over cosine y, tangent y. Okay, so we have a nice formula for the sum of the tangents now. These are really, beautifully simple formulas when you think about it.
anyone remember whether the tangent is an odd or an even function? Odd.
It looks quite odd to me.
Yeah. So if I plug in tangent x plus negative y, right? What's gonna turn negative here? This guy will turn negative. So we have tangent x minus tangent y over 1. Oh, one of these is gonna switch sign. Plus tangent x